Hello, 안녕하세요. My name is SooJean Han, and I am an assistant professor in the School of Electrical Engineering here at KAIST. I am the director of the Autonomous Control for Stochastic Systems Laboratory, where we develop methods for autonomous control by learning patterns. To motivate the kinds of problems that our team is researching, let's take a closer look at the title. So most of you watching this video are probably already familiar with the concept of autonomous control. There's been so many recent developments in the modern day towards autonomous control, such as aircraft formation flight, autonomous driving, and lots of examples in robotics, like the waiter robots that you see in restaurants here in Korea, as well as the Boston Dynamics Atlas robot, and even in science fiction movies like WALL-E and many more. Now, artificial intelligence, AI, in particular, has revolutionized the way we build autonomous systems. And this is because of their good generalization to highly nonlinear dynamics and their ability to handle uncertain and stochastic environments. So lots of recent examples like ChatGPT and OpenAI Figure, Naver's Hyperclova X, Copilot, Gemini, and Tesla's Optimus that you see here on the slide. Now, recently in the 2020s, we've witnessed a boom in AI applications, with recent successes in generative AI models like DALL-E and ChatGPT led to an explosive increase in the investment for a new branch of AI called hyperscale AI for large-scale AI applications. Currently, in order for hyperscale AI to work well, it requires an exponentially increasing number of parameters to train, which in turn requires enormous amounts of data and high-performance computing, such as NVIDIA's Blackwell platform. So the current solution that is adopted by most industries at the forefront of the autonomy revolution, like Google, Tesla, Microsoft, Meta, OpenAI, etc., their solution is, roughly speaking, to increase everything. Increase computing, increase the number of data centers, etc., etc. However, the hyperscale AI era in this direction is currently inefficient. There's large amounts of data that are not always available due to cost, security, and privacy concerns. Gathering large amounts of data is also unsustainable, the biggest bottleneck being power. In order to build more data centers to store more data, we need to drastically increase the cost and power. Gathering large amounts of data is also inefficient because less data-hungry methods for autonomy exist and can be combined with AI. Among the 3 points that are listed at the bottom of the slide, the last point towards improving the data efficiency of autonomy is what we are concentrating on. So that motivates the research of the ACSS lab. We combine both theory and application to develop data-efficient autonomous control methods based on AI, especially for stochastic and uncertain systems. This leads to 2 further directions. Pattern learning, the architecture that you see on the top right of the slide, where we identify and use spatiotemporal patterns for decision-making and control algorithms. At the bottom of the slide, we have the model-based versus model-free trade-off, in which using and approximating a model of the system helps us improve the data efficiency of the model-free part of our algorithm. To understand the details of our research, let's return to the title page. Instead of the autonomous control parts, the key focus of our research is patterns, which can drastically improve data efficiency for autonomous control. Many real-world systems exhibit spatiotemporal patterns. Patterns in time, like vehicle arrival processes over the time and day of week. and patterns in space, such as the network structure in multi-agent systems. Now, a useful measure of data efficiency of an algorithm is the sample efficiency. Geometrical notions of patterns inspired by group theory have been studied before in equivariant neural network architectures, mostly for computer vision applications. So humans typically perform very well on object classification tasks regardless of the pose. As you see in the bottom figure, rotations, scaling, translations, and other versions of those group actions. Rotating those images, for example, you can still correctly determine that the image is of a dog. So what about machines? How do we build machines that do the same thing? We are mostly concerned with sequential decision-making tasks, which further generalize the computer vision types of tasks that mentioned in the previous slide. For example, in robotics, like the robot arm manipulators shown here. Our pattern learning architecture, which I've discussed in the previous slide, is developed under the idea that sequences of states and configurations can be controlled in the same way if they are recognized as patterns. The example shown here at the bottom of the slide is the special case where reflection and rotation symmetries are used to generate patterns of the robot arm. Here is a more concrete application of this concept to the simpler two-link robot arm. The setup is as follows. We're given demonstration data to train a right-handed arm on some task, such as trajectory tracking on a right half plane. And our goal is to see if it is possible to train a separate left arm to perform a reflected task on the reflected left half plane. And the important thing is we don't want to collect any demonstration data about the left arm. Without demonstrations, the most standard way to train the left arm from scratch is using reinforcement learning techniques, such as DQN, deep Q networks. However, this is the most brute force approach because it does not take any advantage of the training that we already did for the right arm. So instead, we consider two methods: pseudo data augmentation, which we call it that way because we're reflecting all of the right arm's demonstration data to train the left arm, and training via symmetric transformations, where we reflect the untrained model of the left arm and use the original demonstration data of the right arm. Then we apply some reflection transformation to the trained model in order to revert it back to the left arm's coordinate space. A sample experiment has been run for comparing the two methods against a baseline which trains the arm from scratch. Results you can see on the right side of the slide. It shows that both methods, PDA and TST, have superior average reward and variance compared to the baseline method. Moreover, the evolution of the reward over time is fastest with TST, the last method, because it only applies a function to the input and output layers of the model based on the reflection symmetry that we've seen before. So there is no need to train anything extra. An important extension that we're currently focusing on is approximate patterns. Exact patterns let us map the original configuration space down to the lower dimensional configuration space, but without any notion of a distance. So as you see in the center of the slide, the reflection symmetry tells you that putting the cup on the left side of the table is the same as putting the cup on the right side of the table due to the reflection and rotation symmetries of the robot arm. However, if you adjust the cup's position slightly towards the center, there is no notion of determining that it is similar to putting the cup on the far right side of the table. So, as a result from math and physics, an important result called Noether's theorem tells us that relating symmetries from conservation laws gives rise to these types of patterns. And extensions are very natural in this case to non-conservative forces. So instead of using only symmetries, we're also looking at similar patterns. And this allows us to map it down to a space, as you see on the right side of the slide, a space which has a distance metric equipped based on the notion of similarity. One important class of applications which uses this notion is large-scaled network control, such as vehicle traffic intersection grids, as you see on this slide. Here, patterns and the approximate patterns are very common due to the natural structure that arises in these intersection networks. We especially emphasize the prediction and memory components of our pattern learning architecture seen before. Here, prediction is used to look at the congestion patterns in the intersection networks, such as weekday, morning, and evening commutes. And common traffic patterns can also be memorized due to the spatiotemporal nature and the structure of the system. Okay. Now, in humans, efficient decision-making from new data can be attributed to the ability to use heterogeneous types of memory, such as long-term and short-term memory, episodic and semantic memory. Here is a comparison of one of our heterogeneous memory architectures against a standard replay buffer that is typically used in reinforcement learning. Episodic memory is used to store patterns that occur frequently enough. Short-term to long-term memory transference is included as an additional filter. In the concrete example of vehicle traffic, the patterns can be chosen as the intersection snapshots with the vehicle counts over time. Approximate patterns can also be built into our memory architecture in the form of equivalence classes. So here, approximate patterns are grouped into the same equivalence class and treated the same way, in the sense that we assign the same control law if they are very similar to each other. Very similar could mean that their distance between the two patterns on the configuration space is less than some epsilon hyperparameter that we choose. As you see on the left side of the slide, memory architectures based on exact patterns for the traffic vehicle example can be mapped down by looking at two rotationally equivalent configurations. You see that the intersection on the left is just a rotation of the intersection in the middle. Memory architectures based on approximate patterns are built using the equivalence classes that I mentioned before. Here you see on the right side of the slide, the traffic intersection pattern is matched up against a similar intersection pattern with one extra car highlighted in red. It's similar intuitively. Here are some simulation results comparing our pattern learning controller against a variety of multi-agent RL implementations. We evaluated it using a variety of congestion metrics as well as data efficiency metrics. By abstracting the traffic patterns in the equivalence classes, you see that the number of memory entries are greatly reduced. This is shown at the top right of the slide, while having similar or even better performance in terms of congestion, such as the average waiting time per car, travel duration per car, and the number of circulating vehicles at the end of the simulation. We have many other applications in development towards the AI-based autonomous control and decision-making by learning exact and approximate patterns using the architecture that we've seen before. So some example applications are robot learning using physical symmetries, data-efficient distributed sensor networks via feedback, and robust and adaptive online planning with uncertainties. The big hope here is we want to mitigate the data consumption issues that are prevalent with AI today. And hopefully, we will get to a more sustainable future with data-efficient autonomy. If you are interested in the work that we are doing, please find links to my personal website and ACSS Research Lab website over here. Thank you.